the universe operates under a profound and quiet division, at the largest scales imaginable, across the vast expanses where galaxies cluster and light bends around massive stars. Gravity rules with absolute geometric precision. This is the domain of general relativity, where space and time form a smooth, continuous fabric that warps under the weight of matter. Yet, when we turn our gaze inward to the subatomic realm, this elegant fabric dissolves completely. At the scale of atoms and subatomic particles, nature is governed by quantum mechanics, a realm of probability, discrete packets of energy, and violent, unpredictable fluctuations. Both of these frameworks are extraordinarily successful, verified by decades of exquisite experimental data, yet they are fundamentally incompatible with one another. When physicists attempt to apply the mathematics of general relativity to the ultra-small scales of the quantum world, the equations collapse into nonsense, yielding results of infinite probability and infinite energy. This mathematical incompatibility is not a trivial detail, but rather the deepest crisis in modern physics. Reconciling immense cosmological mass parameters, compressed inside infinitesimally small spaces, requires simultaneously applying general relativity principles alongside chaotic quantum mechanics equations flawlessly. Current mathematical frameworks collapse entirely during ultimate density epochs, suggesting foundational spacetime concepts might actually represent emergent cosmic illusions rather than absolute realities. String theory attempts resolving this deep existential crisis directly, replacing zero-dimensional point particles with microscopic vibrating strands containing fundamental energy signatures. Transitioning from macroscopic observations toward multidimensional geometric configurations allows physicists to harmonize contradictory mathematical systems into single, beautifully unified frameworks. Multiple theoretical dimensions seamlessly accommodate unique vibrational patterns, effectively determining distinct mass characteristics plus specific electrical charge properties observed throughout particle physics. Furthermore, advanced superstring equations naturally predict gravitational force carriers, known as gravitons, effortlessly bridging historical divisions, separating quantum mechanics from traditional general relativity. Specialized mathematical calculations require exactly 10 or 11 dimensions, preventing catastrophic physical anomalies from destroying foundational string stability profiles within subatomic scales. These hidden spatial dimensions remain tightly curled inside microscopic Calabi-Yau manifolds, rendering extra geometric directions completely invisible toward modern macroscopic observation techniques. Consequently, vibrating strings interact dynamically across complex multidimensional landscapes, generating familiar forces that systematically govern every cosmic interaction experienced worldwide. Physicists continuously evaluate these revolutionary geometric models, looking for subtle cosmological signatures that could definitively prove string vibratory mechanics within deep space environments. Future particle accelerator experiments might eventually discover suspected supersymmetric partner particles, providing vital empirical data regarding overarching multidimensional unification theories. Understanding these hidden energetic vibrations permanently alters collective human perspectives, shifting scientific focus away from traditional matter towards complex, harmonized, cosmic music. But as we resolve the old contradictions, we find ourselves standing before an even greater enigma. If the universe is woven from vibrating strings, what is the medium in which they vibrate, and what determines the music they play? Calm down, relax, subscribe. You're going to want to see where this leads. To understand why our view of the universe is so deeply fractured, we must first look at the foundation of what we believe we understand. In our everyday experience, the world appears solid, continuous, and highly predictable. If you throw a ball, its trajectory is determined precisely by its mass, the force of your throw, and the pull of the Earth. This predictable reality is scaled up to the grandest proportions in Albert Einstein's theory of general relativity. Here, gravity is no longer seen as a mysterious pulling force acting at a distance, but rather as the shape of space and time itself. Imagine a heavy fabric stretched tight, and then imagine placing a large bowling ball in the center. The fabric curves downward. If you roll a smaller marble across the fabric, it will naturally roll toward the center, guided by the curvature. In this view, the sun curves the space around it, and the Earth simply follows the natural path created by that curve. Space-time is smooth, continuous, and beautifully predictable. For generations, this geometric picture satisfied our curiosity about the cosmos, providing a stable foundation for mapping the movements of planets and the expansion of the universe. It tells us that space is a smooth stage upon which the drama of the universe unfolds. However, when we develop instruments capable of peering into the ultra-small structures of matter, this stable foundation begins to tremble. We discover that the material world is made of atoms, which are themselves composed of electrons orbiting a central nucleus of protons and neutrons. As we look closer still, these particles do not behave like tiny planets in miniature solar systems. Instead, they exist in a state of perpetual uncertainty, governed by the laws of quantum mechanics. A particle does not occupy a single, definite position until it is observed. Rather, it exists as a cloud of probabilities. This introduces the first layer of uncertainty into our stable foundation. In the quantum world, things do not happen smoothly. Energy is exchanged in discrete, indivisible packets called quanta. The smooth, predictable curves of general relativity are replaced by a chaotic, jittery landscape where particles pop into and out of existence from the vacuum itself. This contrast creates an intellectual discomfort. We are left with a universe that seems to change its fundamental nature depending on how closely we look. The smooth stage of space and time begins to fray at the edges, suggesting that our elegant, macroscopic descriptions are leaving out a vital, hidden truth about the microcosm. When we observe the cosmos through the lens of classical geometry, we see a tapestry of absolute certainty. The orbits of the planets are calculated with such precision that we can predict an eclipse centuries before it occurs. This predictability relies entirely on the premise that space is continuous, smooth, and empty until matter introduces a localized curve. Albert Einstein formalized this by treating space-time as a dynamic canvas that responds predictably to mass and energy. In this macroscopic view, if you minimize the scale of observation, a small patch of space should look identical to a large patch of space, only empty. It is a harmonious philosophy that suggests reality is orderly at every conceivable level. Yet, when we develop instruments capable of magnifying this canvas to the subatomic scale, this harmonious philosophy faces an irreconcilable contradiction. At the scale of the Planck length, which is approximately 1 decimal point, followed by 34 zeros and a 1 of a meter, the smooth fabric of space-time does not remain calm. Instead, it enters a state of violent, unpredictable motion known as quantum foam. In this micro-realm, the vacuum of space is never truly empty. Instead, pairs of virtual particles and antiparticles constantly fluctuate into existence, borrow energy from the vacuum for an unimaginably brief moment, and then collide and annihilate one another. This behavior is explained by the Heisenberg uncertainty principle, which states that certain pairs of physical properties, such as energy and time, cannot both be known with absolute precision. The shorter the time interval we examine, the greater the uncertainty in the amount of energy present in that region. At the ultra-small scale, this uncertainty becomes so pronounced that the energy can fluctuate wildly enough to spontaneously create matter. Space is no longer a passive, static stage. It is a boiling cauldron of probabilistic events. The deeper implication of this phenomenon is that our traditional concept of a vacuum is entirely incorrect. A vacuum is not the absence of things, but rather a dynamic sea of potentiality, fluctuating between existence and non-existence at every moment. This realization creates an enduring, remaining uncertainty. If the very fabric of space is tearing itself apart at the quantum level through these violent energy spikes, how does it smooth out so perfectly by the time it reaches the scale of human beings, planets, and galaxies? The mathematics of general relativity assumes that space remains smooth, no matter how far you zoom in, whereas the mathematics of quantum mechanics insists that space becomes infinitely chaotic when you zoom in past a certain threshold. When physicists attempt to calculate the gravitational field within this jittery quantum foam, the smooth curves of relativity try to bend around the infinite spikes of quantum energy, causing the equations to spit out answers of infinite curvature and infinite density. This mathematical breakdown tells us that we are missing a fundamental bridge between the large and the small. To understand how physics arrived at this conceptual precipice, we must examine the historical observation of the forces themselves. Throughout the 19th and 20th centuries, the study of the physical world was a process of unification. Scientists discovered that electricity and magnetism, once thought to be entirely separate phenomena, were actually two manifestations of a single force, electromagnetism. This force was responsible for holding electrons in orbit around atomic nuclei, forming the structural integrity of all solid matter. Later, as physicists probed deeper into the nucleus itself, they discovered two more forces operating exclusively at the subatomic level: the strong nuclear force, which binds quarks together to form protons and neutrons, and the weak nuclear force, which mediates radioactive decay. The great triumph of modern quantum field theory was demonstrating that these three forces, electromagnetism, the strong force, and the weak force, could all be described using the same mathematical language. They operate through the exchange of discrete packets of energy which we perceive as particles. This framework treats the universe as a collection of fields permeating space, where particles are simply localized excitations of those fields. When two electrons repel each other, they do so by exchanging a photon, the messenger particle of the electromagnetic field. This system is known as the standard model of particle physics, and its accuracy has been verified to parts per billion in modern particle accelerators. However, this triumphant explanation highlights a glaring contradiction. While three of the fundamental forces fit beautifully into this quantum framework, gravity remains completely isolated. Gravity, as described by general relativity, does not use fields of messenger particles, nor does it operate in discrete packets of energy. It is entirely geometric. It is the shape of the arena itself, not an actor playing on the stage. If we try to force gravity to play by the rules of the standard model, we must invent a hypothetical gravity particle called the graviton. But because gravity responds to mass and energy, and because quantum fluctuations create infinite spikes of energy at small scales, these hypothetical gravitons begin to interact with themselves infinitely, rendering the mathematics completely useless. The deeper implication of this failure is that our classical understanding of gravity and our quantum understanding of matter cannot both be fundamentally true in their current forms. One, or perhaps both, must be an approximation of a deeper, more profound reality. The smooth geometry of Einstein and the jittery particles of the quantum world are like two different languages describing the same mountain, yet neither language possesses the vocabulary to describe the peak where they meet. This leaves us with a profound sense of incompleteness, a realization that our current map of the universe functions perfectly on the coastlines, but dissolves into static when we try to navigate the interior. This brings us to the core of the intellectual crisis. Scientists take this incompatibility seriously because there are places in the universe where these two conflicting realms are forced to interact. Consider the center of a black hole, an object so massive that its gravitational pull prevents even light from escaping. According to general relativity, the entire mass of a collapsing star is squeezed by gravity into an infinitely small point of zero volume, known as a singularity. Because the mass is immense, gravity is infinitely strong, requiring the use of general relativity. But because the volume is infinitesimally small, the object exists at the subatomic scale, requiring the use of quantum mechanics. When we apply both theories to a singularity, the contradiction becomes inescapable. General relativity demands that space be smoothly curved to a point of infinite density, while quantum mechanics insists that at such small scales, the position of the matter must fluctuate randomly due to the uncertainty principle, making an infinitely small point impossible. The two theories actively fight each other at the very heart of a black hole. A similar crisis occurs when we look back to the origin of the universe itself. 13.8 billion years ago, during the first microsecond of the Big Bang, the entire energy of the visible cosmos was compressed into a space smaller than a single subatomic particle. To understand the birth of time and space, we need a single theory that can handle extreme gravity and extreme quantum density simultaneously. Without it, our understanding of the cosmic origin remains a blank page. The deeper implication of this boundary is that space and time may not be fundamental properties of nature at all. If our descriptions of space break down precisely when gravity and quantum mechanics meet, it suggests that space and time are emergent properties, much like temperature. A single atom does not have a temperature. Temperature only emerges when you have a collection of millions of atoms bumping into each other, creating a collective property we measure as heat. In the same way, individual building blocks of reality might not exist in space or time. Rather, space and time might emerge only when trillions of these fundamental building blocks interact on a macroscopic scale. This perspective leaves us with a vast remaining uncertainty. If space and time are not fundamental, what is the underlying fabric from which they emerge? What are the true, indivisible components of reality that exist beneath the quantum foam and beyond the smooth curves of relativity? We are forced to look beyond the idea of particles entirely, seeking a new geometry that can accommodate both the smooth and the rough, the predictable and the chaotic. It is against this backdrop of cosmic fracturedness that physicists began to reconsider the nature of the fundamental building blocks themselves. For centuries, science assumed that if you split matter down to its most basic components, you would eventually find indivisible, zero-dimensional points. This assumption is deeply embedded in the Standard Model, where electrons, quarks, and neutrinos are treated as mathematical dots with no internal structure and no physical size. This point-like nature is precisely what allows for the infinite calculations that ruin our attempts to understand quantum gravity, because two zero-dimensional points can get infinitely close to one another, causing the forces between them to climb to infinity. To resolve this, we must shift our perspective from points to objects with physical extension. If the fundamental pieces of the universe are not dots, but tiny one-dimensional lines or loops, strings, the entire mathematical landscape changes. A string cannot be compressed into a zero-dimensional point. It has a minimum length, a limit beyond which nothing can be divided further. When two strings interact, they do not collide at a single mathematical dot of zero distance. Instead, their interaction is smeared out over a small, finite region of space. This extension naturally dampens the infinite energy spikes of the quantum foam, smoothing out the mathematical calculations and offering, for the first time, a way to calculate the behavior of gravity at the subatomic scale without collapsing into nonsense. This simple shift from a point to a string introduces an extraordinary new explanation for the diversity of the universe. In the Standard Model, every particle is fundamentally different, requiring its own unique set of properties to be programmed into the theory by hand. An electron has a certain mass and charge, a quark has another, and a photon has no mass at all. In string theory, this complex menu of particles is replaced by a single, elegant mechanism. Just as a single string on a cello can vibrate at different frequencies to produce a low, resonant bass note or a high, piercing tone, a fundamental cosmic string can vibrate in different patterns. One vibration pattern makes the string manifest as an electron, with its specific mass and electrical charge. A different vibration pattern makes it manifest as a quark, and yet another produces a photon. The entire universe, from the matter in our bones to the light from distant stars, becomes a grand cosmic symphony played on these tiny, vibrating strands of energy. Yet, this elegant explanation immediately opens up a deeper implication regarding the nature of forces. If particles are simply vibration modes of strings, then the forces that pass between them must also be described by the behavior of strings. When two strings approach each other, they can merge into a single string, or a single string can split into two. This fluid, geometric splitting and joining replaces the violent, point-like particle collisions of old physics. Most remarkably, when physicists solved the equations for how these strings must vibrate, they found that one specific vibration mode always emerged naturally from the math, a massless particle with a spin value of 2. In the language of quantum physics, this is the exact description of the graviton, the theoretical messenger particle of gravity. Gravity is not forced into string theory through complex add-ons. It is an inevitable consequence of the string's existence. This realization brings us back to a profound remaining uncertainty. If these strings are the fundamental components of all matter and all forces, including gravity, what exactly are they made of? A violin string is made of nylon or steel, composed of atoms, which are composed of smaller particles. But a fundamental cosmic string cannot be made of smaller components because it is supposed to be the smallest component itself. It is a strand of pure energy, a localized knot of tension in the fabric of reality. This forces us to confront a difficult conceptual boundary. We are describing a universe made not of substance, but of form and motion, where the appearance of solid matter is merely an illusion created by the rapid vibration of pure geometry. As we contemplate this symphony of strings, we must also recognize that for a string to vibrate in the precise ways necessary to generate the known forces of nature, it requires a specific kind of freedom. A string vibrating in a simple, flat, three-dimensional world cannot produce the complex harmonies required to match the particles we observe in our laboratories. The mathematics of the string's motion becomes unstable, leading to unphysical results and breaking the symmetry of the theory. The equations reveal that the strings are restricted by our limited view of space, hinting that the 3 dimensions we experience are only a fraction of the true arena. This realization shifts our investigation away from the familiar problem of particles and forces and steers us toward the structure of the space in which they move. To understand how these fundamental strands resolve the chaos of the quantum foam, we must look beyond our everyday experience of height, width, and depth. We are forced to ask whether the universe has hidden chambers, extra paths of movement that are invisible to our eyes but completely accessible to the strings. The journey must now move from the nature of the matter itself to the nature of the dimensional stage upon which it dances, leading us directly into the hidden architecture of the universe. Beneath the surface of this apparent contradiction lies a history of hidden mechanisms that scientists have uncovered in their quest for unification. Throughout the 20th century, physicists sought to understand the fundamental forces that govern everything we see. Apart from gravity, they identified three other forces: electromagnetism, which powers our technology and holds atoms together; the strong nuclear force, which binds the cores of atoms; and the weak nuclear force, which governs radioactive decay. Through decades of meticulous observation and experiment, researchers discovered that these three subatomic forces could all be described using the same mathematical language: quantum field theory. In this framework, forces are transmitted by the exchange of tiny messenger particles called gauge bosons. For example, the electromagnetic force is carried by photons, which are packets of light moving between charged particles. This approach culminated in the Standard Model of particle physics, an extraordinarily precise framework that describes all known elementary particles as zero-dimensional points. These point-like particles have no internal structure, no width, and no length. They are simply mathematical dots possessing mass, charge, and spin. To test this view, scientists built massive particle accelerators, crashing bits of matter together at speeds approaching the speed of light to observe the debris. Every experiment confirmed the predictions of the Standard Model with astonishing accuracy. The universe appeared to be a vast cosmic machine, constructed from these point-like entities, interacting through the exchange of force-bearing particles. Yet this deep understanding of the subatomic mechanisms only heightened the isolation of gravity. While the electromagnetic, strong, and weak forces were easily integrated into the Standard Model, gravity stubbornly refused to cooperate. Every attempt to invent a quantum gravity particle, a theoretical messenger called the graviton, resulted in mathematical ruin. When physicists calculated the interactions between these point-like gravitons at very close distances, the equations demanded that the particles could come infinitely close to one another. Because a point has zero size, the distance between 2 points can shrink to absolute zero, causing the gravitational force between them to skyrocket to infinity. The mechanism that worked so perfectly for the other three forces became a mathematical catastrophe when applied to gravity, revealing that treating particles as simple dots might be the fatal flaw in our comprehension of reality. When we look back at the historical framework that allowed us to map the subatomic world, this reliance on point-like dots becomes easily understood. In the mid-20th century, physicists developed a technique called renormalization to handle the infinities that naturally arose in quantum electrodynamics. When calculating the interaction between two point-like electrons, the electric field surrounding each electron grows infinitely strong as the distance between them approaches zero. This is a direct consequence of Coulomb's law, where force is inversely proportional to the square of the distance. To bypass this mathematical barrier, physicists discovered that they could subtract these internal infinities by redefining the mass and charge of the electron using measured experimental values. This mathematical subtraction acted as a shield, allowing scientists to make incredibly precise predictions, despite the underlying point-particle pathology. Yet, when this exact same renormalization mechanism is applied to general relativity, the shield shatters. Gravity is fundamentally different from electromagnetism because gravity responds to all forms of mass and energy. In quantum field theory, as we probe shorter and shorter distances, we require increasingly higher energies, according to the laws of wave mechanics. For electromagnetism, this high energy does not alter the fundamental strength of the force carrier itself in a catastrophic way, but for gravity, energy is the source of the gravitational field. As you zoom in on a zero-dimensional point particle, the high energy required to see at that scale actually breeds more gravity, which in turn demands more energy to calculate, creating an uncontrollable, compounding loop. This introduces a severe contradiction that exposes the limits of our standard models. In quantum gravity, every time a physicist tries to use renormalization to subtract an infinity, a new, more severe infinity emerges from the equations. To cure these new infinities, one would need to introduce an infinite number of independent experimental parameters into the theory, stripping it of all predictive power. A theory that requires an infinite number of adjustments to explain a single interaction is no longer a scientific theory. It is a mathematical confession of ignorance. The explanation for this failure is not that our calculus is weak, but that our foundational premise is flawed. The zero-dimensional point particle is an idealization that nature simply does not support when gravity is brought into the equation. The deeper implication of this failure is that nature must possess a fundamental limit to how small an event can be. If space cannot be divided down to an absolute zero distance without causing our physical laws to explode into infinities, then space itself must be pixelated or quantized at some fundamental layer. There must exist a minimal pixel size in the geometry of reality. This leaves us with a profound remaining uncertainty. If space has a minimal resolution, what happens to our traditional understanding of continuity? If an object cannot move through space smoothly, but must instead hop from one discrete spatial pixel to the next, then the very concept of smooth motion, acceleration, and time must be entirely re-evaluated. To explore how string theory fixes this structural defect without losing the triumphs of past physics, we must examine the physical mechanism of a one-dimensional object moving through space. When a zero-dimensional point particle travels through time, it traces out a simple, infinitely thin line called a world line. When two point particles interact, their world lines intersect at a sharp, definitive point in space-time. This sharp vertex is the exact location where the distance drops to zero and the mathematics collapses into infinity. It is a violent, instantaneous event that leaves no room for error. In contrast, when a one-dimensional string moves through space, it sweeps out a two-dimensional surface called a world sheet. Think of a tiny, closed loop of string drifting through the dark. As time moves forward, that loop traces out a continuous tube. When two strings meet and interact, they do not crash together at a sharp, distinct vertex. Instead, the two tubes smoothly merge into a single tube, forming a shape that resembles a pair of trousers. If you look closely at this merging point, there is no single, definitive moment or location where the interaction begins. The transition is completely smooth, continuous, and distributed across the surface of the world sheet. This geometric smoothing explains why string theory is inherently free from the infinite catastrophes of point-particle gravity. Because the interaction is smeared out over the width of the string world sheet, observers looking at the system from different perspectives will actually disagree on exactly where the strings joined. In quantum mechanics, this observer-dependent smoothing means that the concept of a localized, high-energy collision point disappears entirely. The infinite gravitational spikes that occur when two zero-dimensional dots touch are naturally diluted by the extended geometry of the string itself. The mathematics becomes clean, manageable, and finite, all because we gave the fundamental building blocks a physical size. This shift carries a profound, deeper implication for how we view the elementary forces. In the point-particle paradigm, the messenger particles for the different forces, the photon for electromagnetism, the gluons for the strong force, and the W and Z bosons for the weak force are entirely separate entities, each with its own unique mathematical description. In string theory, these forces are unified by geometry alone. To appreciate the true complexity of orbital accidents, we must first examine the foundational concepts of spaceflight that are widely accepted as common knowledge. Most observers view a rocket as a highly advanced container of liquid or solid fuel designed to generate enough thrust to break free from Earth's gravitational pull. In the public imagination, a space disaster is often perceived as a simple explosion, a sudden and massive release of chemical energy caused by a spark or a ruptured tank. This perspective treats the spacecraft as a conventional vehicle that simply experiences a larger, more dramatic mechanical failure than an automobile or an aircraft. We comfort ourselves with the idea that these events are straightforward instances of mechanical malfunction, easily understood through the lens of everyday physics. This conventional viewpoint establishes a stable foundation for understanding the basic mechanics of propulsion. We know that Newton's third law of motion dictates that for every action, there is an equal and opposite reaction. By expelling mass at high velocity through a nozzle, a rocket accelerates in the opposite direction. The structural design of these vehicles is seen as a robust shield, built to withstand the tremendous forces of acceleration and the intense friction of atmospheric transit. From this baseline, the history of early space exploration seems like a linear progression of increasing engine power and improved structural materials, where safety is merely a matter of reinforcing the hull and perfecting the fuel mixture. However, when we look closer at the actual environment of a launch, the first layer of uncertainty begins to emerge. A rocket leaving the pad is not simply moving through a uniform sky, it is transitioning through a rapidly changing gradient of atmospheric density, acoustic vibration, and aerodynamic shear. The force, known as maximum dynamic pressure, or max Q, represents the precise point where the structural load caused by the vehicle's velocity and the resistance of the surrounding air reaches its peak. At this moment, the spacecraft is subjected to a complex interplay of forces that cannot be fully characterized by simple mechanical equations. The air ceases to behave like a transparent gas and begins to act like a dense, turbulent fluid, buffeting the vehicle with unpredictable frequencies that can find and exploit the tiniest hidden resonance within the structure. This uncertainty challenges the notion that safety can be achieved through brute force engineering. A hull that is made thicker to withstand aerodynamic forces becomes heavier, requiring more fuel, which in turn increases the total energy density of the vehicle and creates greater vibrational stress during liftoff. This feedback loop means that a spacecraft is always balanced on a razor's edge between being structurally inadequate and being too heavy to achieve orbit. The stable foundation of simple mechanical reliability dissolves into a delicate balancing act, where the behavior of materials under extreme dynamic stress becomes highly unpredictable. To understand how this unpredictability manifests, scientists look closely at the phenomenon of micro-yielding within the crystalline structure of aerospace alloys. When a launch vehicle rests on the pad, its structural members experience static loads that are well understood and easily calculated using standard classical mechanics. However, the moment the main engines ignite, the system transitions into a highly dynamic state governed by stochastic, or random, processes. The acoustic energy reflecting off the launch pad strikes the vehicle's skin, sending shock waves through the metal. These waves cause microscopic dislocations within the crystal lattice of the aluminum-lithium panels. While the material may not show any visible signs of deformation, these atomic-level shifts mean that the internal load distribution of the spacecraft is constantly changing, mutating from a predictable engineered structure into an evolving system of localized stress concentrations. This shifting landscape of stress creates an intricate paradox for structural engineers. Standard practice dictates that a component should be built with a safety factor, meaning it is designed to withstand several times the maximum expected load. Yet, in the realm of orbital propulsion, increasing the safety factor by adding mass introduces a hidden penalty. The addition of material alters the natural resonant frequencies of the vehicle. Every structure has specific frequencies at which it naturally vibrates. If the vibrations produced by the rocket engines align with these natural frequencies, a phenomenon known as resonance occurs. The amplitude of the vibrations increases exponentially, potentially causing structural failures at load levels far below the nominal design limits of the material. Thus, the pursuit of structural reinforcement can inadvertently invite catastrophic harmonic amplification. The historical development of high-energy spaceflight provides a clear window into this delicate structural balancing act. During the design of early reusable spacecraft, such as the National Aeronautics and Space Administration's Space Shuttle, engineers had to reconcile the competing demands of thermal protection, aerodynamic control, and structural load management. The outer skin of the vehicle could not be a simple monolithic shield. It had to be an intricate mosaic of thousands of individually molded silica tiles, each bonded to a flexible strain isolator pad, which was in turn bonded to the underlying aluminum structure. This design introduced a vast network of interfaces, each with its own unique thermal expansion coefficient and mechanical compliance. The boundary between materials became a critical zone of vulnerability, where microscopic mismatches in how different substances expand and contract under stress could lead to macro-scale failures. This interface vulnerability reveals a deeper layer of complexity when we analyze how components interact under the influence of acoustic fatigue. During the initial 2 minutes of flight, a spacecraft is subjected to sound pressure levels that exceed 160 decibels, an environment so intense that the acoustic energy itself behaves like a physical force tearing at the vehicle's exterior. This acoustic energy does not strike the hull uniformly. It creates localized pressure fluctuations that rapidly cycle between compression and tension. Under these conditions, the bonding materials holding the thermal protection system to the structure can experience accelerated degradation. The microscopic polymer chains within the adhesives are repeatedly stretched and compressed, a process that can cause them to uncoil and lose their adhesive strength without any outward indication of failure until the structural load reaches a critical threshold. The problem becomes even more acute when we consider the role of aeroelastic flutter. As the vehicle accelerates through the upper regions of the atmosphere, the interaction between the aerodynamic forces and the structural elasticity of the wings, or stabilizing fins, can create a self-excited oscillation. If the structure is too flexible, the energy from the rushing air feeds directly into the vibration of the component, causing the oscillations to grow larger with each passing second. To prevent this flutter, engineers must make the structure sufficiently rigid, but rigidity often requires additional weight or stiffer materials that may be more susceptible to brittle fracture at low temperatures. The design space is restricted by these physical limitations, forcing engineers to operate within an exceptionally narrow corridor where safety is defined not by absolute strength, but by a precise calibration of flexibility and stiffness. This narrow corridor of design parameter stability is continuously threatened by the hidden degradation that occurs over repeated cycles of flight. When a reusable vehicle returns from orbit, it carries with it the invisible scars of its journey. The combination of intense atmospheric heating, vacuum exposure, and cosmic radiation alters the chemical and physical properties of the composite materials and alloys. Microscopic voids, initially smaller than a single micron, can form within the material matrix due to the outgassing of volatile compounds in the vacuum of space. Upon re-entry, the extreme thermal gradient can cause these voids to expand as residual gases or moisture trapped within the structure vaporize, creating internal delamination that remains completely hidden from standard visual inspections. The difficulty in detecting these internal structural changes highlights a fundamental limitation in our observational methodologies. While advanced non-destructive testing techniques, such as ultrasonic scanning and eddy current inspection, are utilized to map the interior of structural panels between flights, these methods are constrained by the resolution of the instruments and the accessibility of the complex internal geometry of the vehicle. A flaw that falls just below the detection threshold of an ultrasonic transducer can serve as the nucleation point for a rapid fatigue crack during a subsequent launch. This reality introduces a profound epistemological challenge. Scientists must accept that the instruments used to verify the safety of a vehicle cannot provide absolute certainty, leaving a residual domain of unknown risk that can only be managed through statistical probability. This reliance on probability rather than absolute certainty shifts our understanding of structural reliability. It forces us to view a spacecraft not as a static object with fixed physical properties, but as a dynamic system that is continuously aging and adapting to its operational environment. The boundary between a safe structure and a compromised one is not a sharp line, but a gray zone where multiple microscopic degradation mechanisms can combine in unexpected ways. For instance, a minor structural vibration that would be completely harmless on a new vehicle can become catastrophic if it coincides with a region of subtle material fatigue or an imperceptible thermal bond degradation. The convergence of these independent factors creates a non-linear response where the total vulnerability of the system is far greater than the sum of its individual parts. This non-linear behavior is further complicated by the environment of microgravity itself, which alters the fluid dynamics and thermal distribution inside the vehicle's plumbing and structural cavities. In the absence of gravity, natural convection ceases. On Earth, warmer, less dense fluids naturally rise, creating a circulating current that helps distribute thermal energy evenly. In orbit, however, heat must be transferred purely through conduction and forced radiation. This means that structural components located near electronics or propulsion systems can develop intense, highly localized thermal gradients. The side of a metallic bracket facing a heat source can become significantly hotter than the side facing the cold interior of the hull, inducing internal thermal stresses that twist and distort the component at a microscopic level, altering its alignment and its ability to bear structural loads during subsequent maneuvers. As we ponder these hidden thermal and mechanical interactions, the stable picture of a robust spacecraft completely dissolves. We begin to see the vehicle as a temporary equilibrium, a complex arrangement of matter that is constantly fighting against the degrading influences of its journey. The traditional engineering philosophy of maximizing strength through mass is revealed to be an incomplete solution, a rustic approach that fails to address the subtle, interconnected realities of high-energy physics. The true challenge of space exploration is not simply building a container strong enough to hold an explosion, but designing an integrated system capable of harmonizing these competing physical forces across vast ranges of temperature, pressure, and vibration. This shift in perspective prepares us to look past the macroscopic architecture of the launch vehicle and focus our attention on the invisible, subsurface boundaries where the true mechanics of failure reside. It invites us to examine the hidden components that operate beneath the metal skin, where the behavior of fluids under high pressure and the resilience of microscopic seals dictate the boundary between a successful ascent and an unpredicted return to equilibrium. The deeper we travel into the structural reality of these machines, the more we realize that the greatest vulnerabilities are often located in the most quiet and unseen places, waiting to be awakened by the immense energies of flight. The investigation naturally moves from the overarching structural frame to the precision boundaries within the internal machinery, where the behavior of materials under extreme pressure introduces the next layer of scientific inquiry. We must now examine the silent mechanisms that govern the containment of these immense energies, focusing on the specialized seals and barriers designed to isolate the destructive chemical processes of propulsion from the fragile biosphere of the craft. It is within these microscopic interfaces that the true boundary between control and chaos is continuously maintained. The real challenge to our understanding emerged when the James Webb Space Telescope directed its massive, gold-coated primary mirror towards seemingly empty patches of the sky. By collecting infrared light that had been traveling through the expanding universe for over 13 billion years, the observatory performed a process called spectroscopy. This technique splits the light into its component colors, allowing scientists to measure its redshift, which indicates exactly how much space has expanded since the light was emitted. The higher the redshift, the further back in time the object exists. The data returned from these deep field observations presented an immediate and stark contradiction to the established models. Scientists identified multiple galaxies at redshifts greater than 10, meaning we are seeing them as they existed less than 500 million years after the Big Bang. According to the accepted timeline, these galaxies should have been small, diffuse collections of a few million stars. Instead, the spectroscopic data revealed that they possessed masses equivalent to tens of billions of suns. They were compact, highly luminous, and contained mature stellar populations that had already converted vast reservoirs of gas into stars. This discovery represents a profound scientific puzzle because it violates the theoretical speed limit of galaxy growth. For a galaxy to achieve such a massive size within a few 100 million years, it would need to convert gas into stars with an efficiency close to 100%, a rate that is physically impossible under our current understanding of stellar feedback. In the modern universe, when stars form, they produce intense radiation and stellar winds that blow away the surrounding gas, effectively shutting down further star formation. The early galaxies seem to have bypassed this regulatory mechanism entirely, packing stars together at an unprecedented velocity. The presence of these fully realized systems in the infant cosmos cannot be easily explained by tweaking minor parameters in our current models. It represents a fundamental divergence between theory and observation, suggesting that the early universe possessed a capacity for rapid self-organization that we do not understand. The contradiction suggests that either our measurements of cosmic time are flawed, or the physical conditions of the early universe allowed matter to behave in ways that are entirely alien to the modern cosmos. To appreciate why this divergence is so profound, one must look at the specific nature of the data that broke the paradigm. When the James Webb Space Telescope directed its infrared spectrograph at these ultra-high redshift targets, it did not just find faint smudges of light that could be explained away as unusual clusters of stars. It captured detailed spectral signatures containing specific absorption and emission features. These features act as a chemical fingerprint, revealing the total mass, elemental composition, and rotational velocity of the observed systems. The data confirmed that these galaxies possessed well-defined stellar disks, mature central bulges, and total baryonic masses that scaled into tens of billions of times the mass of our Sunday. This structural maturity presents an immediate physical contradiction when placed alongside our understanding of cosmic time. To calculate how much matter can accumulate within a specific region of space, astrophysicists use a mathematical baseline known as the accretion rate, which describes the maximum amount of gas gravity can pull from the cosmic web into a galaxy over a given period. Even if one assumes that these early dark matter halos were fed by dense streams of cold gas flowing directly from the cosmic web, a process known as cold stream accretion, the sheer volume of matter observed exceeds what could have physically traveled along those filaments in the 400 million years available. The universe simply had not existed long enough for that much matter to move across those distances at the speed of gravity. Faced with this spatial and temporal bottleneck, some theorists began to question whether our calibration of cosmological redshift itself might be missing a subtle variable. The relation between a galaxy's redshift and its actual chronological age depends entirely on the cosmological parameters we have derived from studying the modern universe and the cosmic microwave background. If the rate of cosmic expansion or the behavior of gravity fluctuated during the first few 100 million years, our conversion from a measured redshift to a specific number of years after the Big Bang could be systematically misaligned. If the timeline itself is stretched, then these galaxies might have had hundreds of millions of years of additional time to assemble, resolving the paradox without rewriting the laws of thermodynamics. However, modifying the expansion timeline introduces an entirely new set of complications that most physicists find highly problematic. The standard cosmological model is not an isolated theory. It is an intricately interconnected web of physics where changing one parameter inevitably destabilizes another. If you alter the expansion rate of the early universe to give these galaxies more time to form, you disrupt the highly precise predictions of Big Bang nucleosynthesis, the process that determined the exact ratios of hydrogen, helium, and lithium created in the first 3 minutes of time. These ratios have been verified to extraordinary precision by local observations, meaning any attempt to fix the galaxy problem by altering the cosmic timeline threatens to break our proven models of nuclear physics. This realization leaves us with the alternative, more radical possibility. The timeline is correct, but the physical conditions of the early universe allowed matter to organize itself through mechanisms that have no modern analog. In the dense environment of the early cosmos, the ambient radiation field was much warmer, and the average density of matter was thousands of times higher than it is today. It is possible that under these extreme, high-density conditions, gas did not behave like the diffuse interstellar clouds we see in our local neighborhood. Instead, it may have undergone rapid, collective gravitational instabilities that allowed entire landscapes of gas to collapse simultaneously, bypassing the slow, step-by-step process of hierarchical assembly altogether. This shift in perspective forces us to abandon the idea of a quiet, slow-motion cosmic dawn and replace it with a vision of an early universe that was incredibly compressed, energetic, and volatile. The mechanisms driving structure formation were not just faster. They may have operated under an entirely different set of thermodynamic rules that favored rapid, large-scale crystallization of matter over gradual accumulation. The contradiction discovered in the deep fields is not a minor anomaly to be swept away with a calibration adjustment. It is a profound signal that the universe possessed an entirely different mode of operation in its youth. As we look deeper into these ancient systems to find out what powered this accelerated organization, we find ourselves confronting an even more specific and challenging manifestation of this early cosmic maturity. The immense mass of these galaxies requires an equally immense source of gravity at their centers to anchor them during such a rapid assembly. This realization shifts our focus from the broad distribution of stars to the dark, hyperdense regions at the very hearts of these primordial structures, where the presence of another cosmic anomaly threatens to break our understanding of physics entirely. As cosmologists wrestled with the impossible mass of these early galaxies, an even deeper mystery began to materialize within the data. Inside many of these ancient systems, the intense luminosity was not coming from stars alone, but from active galactic nuclei. These are the supermassive black holes sitting at the cores of galaxies, actively devouring surrounding matter and emitting torrents of high-energy radiation across space. The James Webb Space Telescope detected these active black holes at redshifts corresponding to a time when the universe was in its absolute infancy. The existence of a supermassive black hole at this early stage introduces a profound breakdown in our understanding of astrophysical physics. A black hole grows by pulling matter into its event horizon, but as this matter falls inward, it compresses, heats up, and radiates immense energy. This radiation exerts an outward pressure known as the Eddington limit, which naturally restricts the rate at which the black hole can consume matter. If a black hole feeds too quickly, its own radiation blows the food supply away. Calculating back from these early observations, a black hole starting as a remnant of the first generation of stars would not have had enough time to reach millions of solar masses while respecting this limit. This breakdown in current theory suggests that the seeds of these supermassive black holes must have been incredibly large from the very beginning. One competing idea is the direct collapse hypothesis, which proposes that massive clouds of primordial gas skipped the star stage entirely, collapsing directly under their own immense gravity to form black holes with masses of 100,000 suns instantaneously. While this theory provides a potential pathway, it requires highly specific, pristine conditions where the gas cloud is heated by nearby radiation to prevent it from fragmenting into ordinary stars, a scenario that remains unverified. The growing uncertainty surrounding these observations leaves us facing a universe that appears far more mature than its age should allow. If both galaxies and black holes were able to grow at rates that defy our laboratory-tested models. For generations, the story of our universe has been told as a gradual, orderly progression from simplicity to complexity. We have long understood that the universe began in a state of extreme heat and density approximately 13.8 billion years ago. In the immediate aftermath of this initial expansion, space was remarkably uniform, consisting of a nearly perfectly smooth distribution of hydrogen and helium gas. There were no stars, no planets, and no galaxies, only a vast, dark expanse cooling as it expanded outward. This period, known as the Cosmic Dark Ages, lasted for millions of years, a time of absolute stillness before the first light broke across the cosmos. The traditional model of cosmic evolution relies on the principle of hierarchical structure formation. This framework states that small objects formed first, and larger objects were built over vast stretches of time through successive mergers. Tiny fluctuations in the density of the early universe, where matter was slightly more concentrated, acted as gravitational seeds. These seeds slowly pulled in surrounding gas, eventually becoming dense enough to ignite the first generation of stars. These early stars were thought to be isolated and primitive, slowly gathering into small clusters, which would then collide and merge over billions of years to form the large, majestic spiral and elliptical galaxies we observe in our local universe today. This gradual model provided a comfortable and intuitive view of history, suggesting that the complexity we see around us is the product of slow, patient accumulation. It allowed scientists to construct a timeline where the universe spent its youth quietly organizing itself, moving methodically from disorganized gas to structured star systems. This understanding was supported by observations from ground-based telescopes and earlier space observatories, which showed that as we look further away, and therefore further back in time, galaxies generally appear smaller, more irregular, and less developed than those nearby. Yet, this foundational stability began to show subtle signs of strain as our observational technology advanced. Even before the launch of the James Webb Space Telescope, deep sky observations had occasionally detected mature galaxies and massive black holes at distances that pushed the limits of the hierarchical model. These early anomalies were often dismissed as rare outliers or statistical fluctuations, but they introduced a persistent layer of uncertainty. They hinted that the early universe might have been far more efficient at organizing matter than our models allowed. raising the quiet, troubling possibility that our gradual timeline of cosmic history was incomplete. To appreciate the gravity of this uncertainty, one must understand how firmly the standard cosmological model, known as lambda cold dark matter, has held sway over modern astronomy. For decades, this framework provided an elegant explanation for the large-scale structure of the universe. It posited that dark energy, represented by lambda, drives the accelerated expansion of space, while slow-moving, cold dark matter provides the gravitational scaffolding necessary to pull ordinary baryonic gas together. In this cosmic ballet, everything follows a strict chronological order. It takes time for dark matter to clump into halos, more time for baryonic matter to fall into those halos, and even longer for that gas to cool sufficiently to form the first generations of stars. This structured pacing was verified by observations of the cosmic microwave background, which showed that the infant universe was remarkably uniform, with density variations of only 1 part in 100,000. When astronomers began pushing the limits of the Hubble Space Telescope and deep ground-based observatories, they expected to see the early stages of this slow gathering process. Instead, they occasionally encountered bright, compact points of light at high redshifts that did not fit the expected evolutionary curve. These objects appeared at a time when the universe was less than 1 billion years old, yet their light profiles suggested they harbored massive stellar populations. The initial reaction within the scientific community was one of cautious skepticism. When working at the absolute limit of detection, where a galaxy appears as nothing more than a few pixels on a highly sensitive charge-coupled device, errors can easily manifest. Errors. A galaxy that appears very distant due to its red coloration might actually be a closer, intrinsically redder galaxy covered in cosmic dust, or a foreground object whose light has been distorted. However, as these distant anomalies accumulated, it became increasingly difficult to attribute them all to observational artifacts. Astronomers utilized a technique known as photometric redshift estimation, which uses broad filters to gauge the color and distance of a galaxy based on the drop in its light output at specific wavelengths. While this method is highly efficient for surveying thousands of galaxies simultaneously, it possesses an inherent margin of error. It provides a statistical probability of distance rather than an absolute certainty. Because the standard model was so robustly verified by other independent lines of evidence, it was statistically more logical to assume these early, massive galaxies were either misidentified foreground objects or rare statistical flukes occupying the extreme, highly unusual tail of a standard distribution curve. Yet, the persistent detection of these high redshift objects created an undercurrent of tension. If even a fraction of these observations were accurate, it implied that the universe was capable of producing highly evolved systems much faster than standard gas dynamics and gravitational collapse should allow. In our local universe, star formation is a self-limiting process. When a massive star ignites, it releases powerful stellar winds and intense ultraviolet radiation that heats the surrounding interstellar medium, pushing the remaining gas away and preventing it from collapsing into new stars. This negative feedback loop acts as a cosmic brake, ensuring that galaxies convert their gas reservoirs into stars gradually over billions of years. The early anomalies hinted at an environment where this brake was somehow disengaged, allowing for an unprecedented efficiency in stellar manufacturing. This tension highlighted a deeper limitation in our historical observational methodology. The Hubble Space Telescope, while a magnificent instrument, was primarily optimized to view the cosmos in ultraviolet and visible light. Because the expansion of the universe stretches the wavelength of light as it travels across vast distances, a phenomenon known as cosmological redshift, the ultraviolet and visible light emitted by the first stars and galaxies is shifted entirely into the infrared spectrum by the time it reaches Earth. Hubble could only peer so far into the infrared before its own warmth blinded its instruments. To truly see the cosmic dawn, humanity required an observatory that could operate at temperatures close to absolute zero, shielded from the thermal radiation of the Earth and the Sun, equipped with a mirror large enough to collect the incredibly faint, stretched photons of the primordial universe. The realization that our view of the early universe was fundamentally limited by the infrared barrier shifted the scientific focus from dismissal to anticipation. Astronomers recognized that the anomalies detected by older instruments were not necessarily errors, but signposts pointing toward an unexplored epoch of cosmic history. These distant objects stood as silent challenges to the completeness of our cosmological timeline, suggesting that the transition from a smooth, the featureless sea of hydrogen gas to a highly structured cosmos was far more rapid and dynamic than our models had assumed. The stage was set for a deeper investigation, one that would require leaving the comfort of our established theories to look directly into the absolute darkness of the infant universe, where the first structures were waiting to be revealed in their true proportions. This shifting perspective brings us to the threshold of a new observational reality, where the ambiguities of early deep sky surveys give way to precise, undeniable data. As we prepare to examine the physical processes that operated within these ancient systems, we must confront the possibility that the mechanisms of cosmic growth are far more complex than a simple, gradual accumulation of matter over time. The journey ahead leads us away from the familiar, orderly progression of the modern universe and down a path toward the hidden interactions that shaped the very architecture of the cosmos, where the next layer of mystery awaits our analysis. To understand how these ancient structures could exist, we must look beneath the surface of what is visible and examine the hidden physical mechanisms that govern the behavior of primordial matter. The primary force driving the architecture of the cosmos is gravity, but gravity does not operate in a vacuum. In the early universe, ordinary matter was intimately intertwined with dark matter, an invisible substance that interacts only through gravitational pull. Dark matter formed a vast, invisible scaffolding, collapsing into immense spherical structures called halos, long before ordinary gas could cool and settle. These dark matter halos served as the cosmic crucibles where the first structures were forged. Ordinary hydrogen gas was drawn into the deep gravitational wells of these halos, gaining kinetic energy as it fell toward the center. However, for a galaxy to form stars, this gas must lose its energy and cool down. Without an efficient cooling mechanism, the gas remains too hot and energetic to compress under its own gravity. In the modern universe, heavy elements like carbon, oxygen, and iron act as efficient coolants, radiating heat away into space. But in the primordial universe, these elements did not yet exist. The gas was pure hydrogen and helium, which cool much less efficiently. Historical discoveries in the late 20th and early 21st centuries revealed that primordial gas could only cool by forming molecular hydrogen, a process that is agonizingly slow and requires specific physical conditions. This suggested that star formation in the early universe should have been a heavily bottlenecked process, occurring at a leisurely pace. Astronomers calculated the maximum rate at which gas could fall into dark matter halos, cool, and ignite into stars, establishing a theoretical speed limit for galaxy growth. This speed limit formed the basis for all modern computer simulations of the cosmos. This detailed understanding of gas dynamics and dark matter interactions created a highly consistent picture of the early universe, yet it left a critical question unanswered. If the cooling of primordial gas is inherently inefficient, and if the cosmic speed limit for structure formation is fixed by these fundamental physical processes, how could any structure overcome these limitations to grow rapidly? The mechanisms we observed in our local universe seemed ill-equipped to explain how massive systems could develop during the earliest epochs of time, suggesting that some undiscovered process was operating in the dark. To comprehend the nature of this hidden process, we must first examine the invisible architecture that dark matter established long before the first star ever ignited. In the immediate aftermath of the initial cosmic expansion, ordinary matter remained tightly coupled to the intense ambient radiation field, preventing it from collapsing under its own gravity. Dark matter, however, was unaffected by this radiation pressure. It began to pull itself together into vast, diffuse concentrations known as dark matter halos, creating the underlying gravitational framework of the universe. When the cosmos cooled sufficiently for ordinary matter to decouple from radiation, this ordinary gas found itself drawn into the pre-existing gravitational valleys created by the dark matter. As primordial gas fell into these dark matter halos, it gained immense speed, converting its gravitational potential energy into kinetic energy. This acceleration caused the gas to collide with itself, generating shock waves that heated the interior of the halos to temperatures scaling into thousands of kelvins. This extreme heat presented an immediate physical paradox for the formation of galaxies. A gas cloud that is intensely hot possesses high thermal pressure, causing its particles to move rapidly and push outward against the pull of gravity. For gravity to win the struggle and compress this gas into the dense cores required to ignite stars, the gas must somehow shed its thermal energy. It must cool down, yet the universe at this stage lacked the very tools it uses to cool itself today. In the modern cosmos, the interstellar medium is enriched with heavy chemical elements synthesized by generations of stars, such as carbon, oxygen, neon, and iron. These heavy elements possess complex electronic structures that allow them to absorb thermal energy through collisions and radiate it away as infrared photons, which easily escape into the vacuum of space. This cooling pathway is highly efficient, allowing modern gas clouds to drop to temperatures just a few degrees above absolute zero, where gravity can easily fracture the cloud into thousands of sun-like stars. But in the primordial era, the universe was entirely pristine. There were no heavy elements, only a vast, uniform mixture of hydrogen and helium, elements that are notoriously poor at radiating heat away at lower temperatures. The only available cooling agent in the early universe was molecular hydrogen, a fragile compound formed by the rare pairing of two hydrogen atoms in the dark. Unlike heavy atomic elements, molecular hydrogen is a very inefficient coolant, capable of radiating energy only when the gas is hotter than a few hundred kelvins. Once the temperature drops below this threshold, the molecular hydrogen can no longer be excited by collisions, and the cooling process grinds to an absolute halt. This fundamental limitation established what cosmologists long considered an unbreakable speed limit on cosmic structure formation. Galaxies could only grow as fast as their primordial gas could slowly, meticulously radiate its heat through this inefficient molecular gateway. This theoretical speed limit formed the bedrock of all cosmological simulations for decades. Computer models programmed with these laws of thermodynamics predicted that the first galaxies would be small, fragile, and slow to mature. They were expected to be loose collections of primitive stars, growing only by increments as they drifted across space and occasionally collided with neighboring systems. The physics of molecular hydrogen dictated that the transformation from a hot, ionized fog into a well-organized, massive galaxy should require hundreds of millions, if not billions, of years of patient gravitational assembly. Yet this consistent picture left an unacknowledged vulnerability at the core of our theories. The models assumed that the conditions within early dark matter halos were uniform and quiet, free from external disruptions. They did not fully account for how these systems would react if the density of the early universe drove interactions at a pace that bypassed the standard cooling bottlenecks entirely. If a mechanism existed that could compress gas faster than it could heat up, or if an undiscovered phase of cosmic evolution altered the behavior of ordinary matter within those invisible dark matter wells, the cosmic speed limit would be rendered obsolete. The persistence of this physical puzzle shifts our focus toward the early environment itself, forcing us to consider whether our local observations have blinded us to the true potential of the primordial cosmos. As we move closer to analyzing the actual data returned from the cosmic dawn, we are compelled to look for evidence of a breakdown in these thermodynamic rules. The journey now carries us toward the first direct observations of these ancient systems, where the elegant simplicity of our gas cooling models encounters the messy, undeniable reality of a universe that refused to wait for permission to grow. The elegance of the Schrödinger equation, which so beautifully describes the smooth, continuous evolution of a probability cloud, contained within it a quiet, unsettling monster, the problem of collapse. If the wave function governs all quantum entities, and everything is ultimately made of quantum entities, then where, exactly, does the quantum world end and the classical world of certainty begin? This question, this profound gap between possibility and fact, drove the equation's own creator, the gentle physicist Erwin Schrödinger, to devise a conceptual nightmare designed to demonstrate the inherent absurdity of applying the rules of the microcosmos to the world of cats and clocks. Imagine now, in the stillness of this late hour, the construction of this infamous thought experiment. You place a living, breathing cat inside a perfectly sealed, opaque steel chamber. Alongside the cat, you install a delicate apparatus, a single radioactive atom that, within a period of 60 minutes, has precisely a 50% probability of decaying and a 50% probability of remaining stable. This is our quiet quantum coin flip, the engine of uncertainty. Attached to this atom is a Geiger counter, set up to detect the decay event. If the atom decays, the counter triggers a small hammer, which immediately smashes a tiny vial of prussic acid, a lethal poison. If the atom does not decay, the hammer remains still, and the cat remains perfectly healthy. The atom, according to the principles of the wave function that we explored, exists in a state of superposition until it is measured. It is simultaneously decayed and not decayed. Its probability cloud, the smear of potential, holds both realities in equal measure. But here is where the absurdity quietly settles in, forcing a contradiction upon your logical mind. The fate of the entire macroscopic apparatus, the hammer, the vial, the poison, and, critically, the cat, is directly, mechanically linked to the quantum state of that single, subatomic particle. The rules of quantum mechanics dictate that as long as the box remains sealed, the entire system must be described by a single, encompassing wave function that smoothly evolves over time, following the logic of the elegant equation. Therefore, until an external observer opens the steel chamber and performs the final measurement, the cat itself must be described by a superposition state. In this strange, mathematical sense, the cat is simultaneously an extremely unhappy, dead cat and a perfectly healthy, living cat. a duality that is utterly meaningless in the world of our lived experience. The concept of an entity being both alive and deceased at the same time is the ultimate defiance of the principle of non-contradiction, the fundamental cornerstone of classical reality. Schrödinger intended this thought experiment to be a subtle piece of scientific humor, a reductio ad absurdum that exposed the incomplete nature of the theory. The particle refuses to make eye contact not just with the detector, but with the poor feline locked in the box. The paradox compels us to ask, at what point did the reality solidify? Did the wave function collapse when the atom decayed? Or when the Geiger counter registered the decay? Or when the hammer moved? Or only when the scientist, having waited precisely 1 hour, opened the box to look inside? If you choose the latter, you are granting a profoundly powerful, almost cosmic role to the act of observation, suggesting that the consciousness of the physicist is what performs the final cut, splitting the probability pool into a single, undeniable fact. If you choose an earlier moment, say, the moment the Geiger counter registered the click, then you must acknowledge a moment when the quantum uncertainty was transferred to the macroscopic world, only to disappear instantly. The measurement problem is thus revealed as the problem of defining the boundary between the smooth determinism of the equation and the sudden, random commitment to fact. This paradox forces a quiet revolution in our thinking about reality. It implies that the world we perceive, the world of definite outcomes, must be continuously created, moment by moment, through endless, instantaneous collapses. The only difference between the electron in the double-slit experiment and the cat in the box is the sheer scale of the possibilities. For the cat, the possibilities are only 2 dead or alive, while the electron possesses an infinite gradient of potential locations. Yet, the governing principle remains the same. Reality is potential until it is witnessed. The scientific community has, over time, developed theories that attempt to solve this uncomfortable absurdity, most notably through the concept of decoherence, a process we will explore later in our quiet journey. Decoherence suggests that the superposition of a large, complex system like a cat is instantly and irrevocably destroyed by its interaction with the incredibly vast number of particles in its environment, the air, the heat, the photons inside the box. These environmental interactions perform countless silent measurements every picosecond, effectively collapsing the wave function so rapidly that the cat never truly gets to experience its bizarre duality. For all intents and purposes, the cat is quickly forced to choose a singular fate by the sheer noise of its environment, thereby maintaining the illusion of a classical, certain world. But even if decoherence explains why we never see a blurry, half-dead, half-alive cat, it does not erase the foundational truth revealed by the box. The underlying reality is governed by potential. The universe is composed of possibilities, and only through the relentless interactions and commitments of measurement do we experience the rigid, seemingly factual world of our daily lives. This thought experiment stands as a silent monument to the power of quantum weirdness, a humorous yet profound challenge to the very definition of being. To understand this challenge fully, we must now turn our attention from the spatial paradox, the particle existing in 2 places, to the temporal paradox, the idea that quantum events can be linked across vast distances with 0 time lag. This non-local connection, this strange, instantaneous tether between particles that have once interacted, takes us even further away from the comfortable logic of the classical world. we must investigate the relationship that Albert Einstein famously and humorously called spooky action at a distance. Our quiet exploration of the deeper structure brings us to a final, profound echo from the wellspring of Western philosophy, an image devised over 2 millennia ago that serves as a chillingly accurate metaphor for the difference between the classical, perceived world and the true, quantum reality, Plato's allegory of the cave. This allegory, contained within Plato's great dialogue, The Republic, asks us to contemplate whether our sensory experience is merely a pale, derived version of a richer, more fundamental truth. Imagine yourself now among the quiet prisoners, chained, since birth, in a deep, dark cavern. Their necks and legs are fixed, forcing them to look only forward, at the back wall of the cave. Behind them, unseen, a fire burns, and between the fire and the prisoners, others walk, holding up various artificial objects, statues, and figures. The only thing the prisoners can ever see, hear, or know are the 2-dimensional shadows cast by these objects onto the wall before them. They would name the shadows, categorize them, and believe, with absolute certainty, that these flat, flickering forms constitute the entirety of true reality. Their science, their common sense, their shared life experience, all are based on the deterministic, singular nature of the shadows. This world of shadows is the classical, Newtonian world of our macroscopic experience. It is the world where objects have definite properties, where causes strictly follow effects, where time moves forward predictably, and where all reality seems to be composed of fixed, distinct facts. The shadow of a statue, for instance, has a definite size and location. It is either here or there, and it follows a clear, linear trajectory across the wall. The prisoner's intuition, like that of the classical physicists, is one of certainty, locality, and fixed outcomes. Now, contemplate the true objects and the firelight behind them. These unseen, 3-dimensional entities, the statues and figures that cast the shadows, represent the underlying, fundamental reality, the quantum world. The quantum world is inherently richer, more complex, and vastly different from its projected shadow. An electron, before observation, is not the point-like shadow the detector registers. It is the complex, shimmering, multi-dimensional reality of the wave function, simultaneously occupying many potentials, a cloud of possibility that exists in a strange, abstract space we call Hilbert space. When a quantum measurement is performed, the moment we look at the electron, it is analogous to the light from the fire hitting the 3-dimensional object and projecting a single, flat shadow onto the wall. The act of observation is the act of projection, reducing the rich, probabilistic, high-dimensional reality of the wave function, the true object, into the singular, definite, low-dimensional reality of the classical fact. The shadow, the collapse of the wave function, is simply the process of flattening the true object into a mere silhouette. The quiet, subtle humor of the situation lies in the quantum particle's inherent refusal to be a single, flat shadow until forced. As long as the electron remains unmeasured, it maintains its full, 3-dimensional, wave-like existence. The moment we try to find its definite position, we force it to cast a shadow on the wall of our perception. And what is the Heisenberg uncertainty principle? but the unavoidable blurring that results from trying to define a three-dimensional object too sharply by its two-dimensional projection. You cannot know the true object's full depth and its exact motion simultaneously merely by looking at its shadow. Plato's allegory also provides a profound, subtle understanding of entanglement. If two statues, two true objects, are linked together such that if one moves, the other must instantly move in the opposite direction, their shadows on the wall would also be perfectly, instantaneously correlated. To the prisoners, this would seem like spooky action at a distance between two shadows, as if one shadow magically influences the other without communication. But the person who has left the cave, the liberated philosopher, knows the truth. The correlation is not due to a communication between the shadows, but to the single, shared, unseen reality of the true, linked objects behind them. Entanglement, in this quiet, philosophical sense, is merely the perception of a single, indivisible quantum reality from our position as chained observers of shadows. This ancient framework offers a path to a quiet acceptance of quantum mystery. The strangeness of the quantum world is only strange when viewed from the perspective of the shadow world of fixed facts. If we accept that the wave function, the probabilistic field, is the fundamental reality, the forms, in Plato's original language, the true objects of the cosmos, then the classical world, the world of certainty and definite outcomes, is merely the inevitable, simplified image cast by that deeper structure onto the wall of our sensory experience. We are all quiet prisoners, shackled by the unavoidable interaction of decoherence, forced to perceive the universe as a series of simple, distinct shadows. But through the subtle mathematics and the precise experiments of the modern physicist, we gain a brief, profound glimpse of the true, flowing, multidimensional light source behind us. The purpose of this entire quiet documentary is to unchain your mind just enough to sense the full reality of the true objects, to hear the soft whispers of the probability fields just beyond the two dimensions of the shadow wall. This quiet, contemplative understanding of reality's hidden depths now provides the conceptual lens through which we can explore more of the deeper structure. We will now turn our attention from philosophical models back to the most bizarre, active behaviors of the quantum particle, the phenomena that truly defy the classical logic of the shadows, beginning with the astonishing act of passing through a wall. Beneath the visible events of a launch vehicle's ascent lie the intricate, microscopic processes that dictate the behavior of matter under extreme thermal and mechanical gradients. To understand the hidden mechanisms of space disasters, we must look at how materials respond to changes that occur at the molecular level. During the development of the Space Shuttle program, engineers relied heavily on elastomeric polymers to seal the joints between the segments of solid rocket boosters. These synthetic rings, known as O-rings, were designed to expand rapidly and seal any gaps created by the immense pressure of ignition, preventing the escape of superheated gases that exceed 2000 degrees Celsius. The critical observation that transformed our understanding of these materials was the discovery of how temperature alters the elasticity of polymers. As an elastomer cools, its molecular chains lose their flexibility, transitioning from a resilient, rubbery state to a rigid, glassy state. This phenomenon, known as the glass transition temperature, occurs silently and without any visible alteration to the material's appearance. On a cold morning in January 1986, the ambient temperature at the launch pad caused the O-rings of the Space Shuttle Challenger to sink below this critical threshold. When the solid rocket motors ignited, the flattened rings could not recover their shape quickly enough to fill the expanding gap in the joint, allowing a plume of incandescent gas to escape and erode the adjacent structural matrix. This microscopic failure immediately triggered a macroscopic chain of events governed by fluid dynamics and thermal energy transfer. The escaping gas acted like an industrial plasma torch, cutting through the aluminum skin of the solid booster and burning into the external fuel tank, which contained hundreds of thousands of liters of liquid hydrogen and liquid oxygen. As the structural integrity of the tank failed, the aerodynamic forces acting on the vehicle caused it to rotate abruptly away from its optimal flight path. At speeds exceeding Mach 1.5, the atmosphere became an immovable wall, and the vehicle was torn apart not by a centripetal explosion, but by extreme aerodynamic shear. The investigation into this event forced scientists to look deeper into the historical behavior of these seals under less severe conditions. Research revealed that during previous warmer launches, the O-rings had routinely experienced a phenomenon called soot blowout and minor erosion, where hot gas briefly bypassed the first line of defense before the material could fully seat. These quiet observations had been categorized as an acceptable risk within the operating parameters of the vehicle, a psychological and bureaucratic shift that researchers later termed the normalization of deviance. This concept describes how a recurring anomaly is gradually accepted as a normal characteristic of a system, blinding observers to the hidden mechanism that is slowly eroding the safety margin towards zero. To understand how this erosion of safety happens mechanically, we must examine the physical process of joint rotation within solid rocket boosters during the first few milliseconds of ignition. When the solid propellant inside the booster is ignited, the internal pressure rises from atmospheric levels to over 6 megapascals in less than 1/3 of a second. This rapid pressurization causes the steel casing of the booster to expand outward. However, because the booster is manufactured in segments that are pinned together at specific joints, the tang and clevis configuration of these joints reacts to the pressure by bending slightly. This localized bending, known as joint rotation, actually pulls the sealing surfaces away from each other, widening the gap that the elastomeric O-rings are designed to fill. The primary defense against this widening gap is the resiliency of the elastomer itself. In a perfectly functioning system, the internal pressure of the gas acts upon the backside of the O-ring, forcing it into the sealing track in a process called extrusion. This mechanical design relies on the fluid-like behavior of the rubber under high pressure. It must deform instantly to track the moving metal surfaces. But this deformation requires the molecular chains within the elastomer to slide past one another without resistance. If the material's internal temperature is too low, the kinetic energy of these polymer chains is diminished. Instead of behaving like a highly responsive fluid, the elastomer behaves like a sluggish solid. The gap opens faster than the frozen O-ring can expand to meet it, creating a temporary pathway for superheated gas. This temporary pathway allows a high-velocity stream of combustion products traveling at supersonic speeds to blast past the primary seal. As this gas encounters the colder metal of the joint, it experiences rapid cooling, leaving behind a telltale residue of carbon particles. This is the phenomenon known as soot blowout. In the context of previous launches, the presence of this soot was viewed not as a critical warning sign of a transient sealing failure, but as proof that the secondary O-ring, located just downstream from the primary, was successfully performing its backup function. The system was performing as intended by its design redundancies, or so it appeared on the surface. The contradiction within this interpretation lies in a fundamental misunderstanding of how erosion occurs in high-energy gas streams. The hot gas does not simply pass through the gap, it actively transfers thermal energy into the surface of the elastomer through convection. At temperatures exceeding 2000 degrees Celsius, the polymer structure undergoes immediate thermal degradation, a process called ablation. The surface of the O-ring is vaporized, carving a physical channel or pit into the circular seal. This erosion reduces the cross-sectional diameter of the ring, permanently diminishing its ability to maintain a positive seal, even if the material later warms up due to friction. Each microsecond, the gas remains unsealed. The erosion deepens, following a non-linear acceleration curve toward total failure. This realization exposes a deeper implication regarding the nature of redundancy in complex engineering. When a system is designed with a primary and a secondary seal, the underlying assumption is that these two components are statistically independent. If the primary fails with a certain low probability, the secondary provides an independent line of defense, squaring the safety margin. However, in an operational spaceflight environment, the factors that cause the primary seal to fail, such as low ambient temperature or extreme joint rotation, apply equally to the secondary seal. The independence of the redundant components is an illusion. When the primary O-ring is bypassed, the secondary O-ring is instantly subjected to an even more severe thermal and aerodynamic load than the primary was designed to handle, changing the system from a redundant configuration to a single point of failure with no remaining margin. The remaining uncertainty that haunted the engineering teams lay in their inability to precisely model this transient sealing phase. In the late 20th century, computer simulations could not fully replicate the coupled thermodynamic, fluid, and structural interactions occurring inside a mutating joint within a fraction of a second. Engineers were forced to rely on empirical testing, firing subscale motors on horizontal test stands. These static tests, however, were conducted under ideal conditions where the structural loads of a vertical launch vehicle, including the weight of the external tank and the twisting forces of the main liquid engines, were absent. The data gathered was clean, but it was disconnected from the chaotic reality of an actual operational launch profile. This disconnect between laboratory data and operational reality allowed the normalization of deviance to flourish within the organizational structure managing the program. When an anomaly is observed but does not result in a catastrophic loss, the engineering mind can unconsciously recalibrate its baseline of what constitutes acceptable performance. The presence of minor O-ring erosion on early missions was classified as an expected operational characteristic, an inherent nuance of the hardware rather than a systemic flaw. The safety margin was not a fixed, immutable boundary, but a malleable concept that was slowly compressed by a series of successful flights, creating a false sense of security that masked the approaching thermodynamic threshold. This psychological mechanism is deeply linked to the behavior of materials under prolonged stress. Just as a metal component can undergo fatigue through repeated cycles of load, an engineering organization can undergo a form of analytical fatigue, where its sensitivity to warning signs is gradually blunted by the absence of negative outcomes. The data indicating danger becomes indistinguishable from background noise because the system has survived similar levels of degradation before. This feedback loop is exceptionally dangerous because it ensures that the system will continue to fly until it encounters a set of environmental conditions that pushes the degradation past the hidden threshold of total structural collapse. The transition from this organizational and material blindness leads us directly to the next phase of our investigation, where we must confront how these hidden mechanisms operate when the scale of the system is altered. The vulnerabilities discovered within the solid rocket booster joints were not isolated incidents. They reflected a broader, more systemic challenge in how human engineering interacts with the extreme energy states required for orbital transport. As we move forward, we must look at how these subtle, microscopic failures can be magnified across different operational regimes, exploring what happens when a design flaw is carried into the intense, transformative environment of atmospheric re-entry, where the forces acting on the vehicle are no longer driven by internal chemical propulsion, but by the raw kinetic energy of cosmic velocity. The realization that minor anomalies can accumulate without causing immediate failure presents a profound scientific puzzle. It introduces a major contradiction to the traditional philosophy of risk analysis, which assumes that past success is a reliable indicator of future safety. If a system operates successfully multiple times despite experiencing unexpected component degradation, classical logic suggests the design is resilient. However, complex systems analysis reveals the opposite. Each successful flight with a known flaw merely masks a non-linear path toward a catastrophic threshold. The puzzle deepens when we realize that the evidence of danger is often present in the data but remains unreadable because our analytical models are looking for the wrong signals. This contradiction is vividly illustrated by the events surrounding the loss of the Space Shuttle Columbia in 2003. During the initial seconds of launch, a piece of lightweight insulating foam, roughly the size of a suitcase, detached from the external tank and struck the leading edge of the left wing. This foam was part of the thermal protection system, designed to prevent ice from forming on the ultra-cold surface of the liquid fuel tanks. Because the foam possessed a very low density, it seemed counterintuitive to many observers that it could cause significant damage to the reinforced carbon-carbon panels that shielded the wing from the heat of re-entry. To understand how a satellite functions, we must first dismantle the common misconception of what it means to be in space. Most people view space as a place where gravity simply ceases to exist. We see videos of astronauts floating effortlessly inside the International Space Station or tools drifting away into the void, and we naturally assume they have traveled beyond the reach of Earth's gravitational pull. This is a profound misunderstanding of the physical reality. At an altitude of 400 kilometers, where many satellites operate, the gravitational force of the Earth is still approximately 90% as strong as it is at sea level. If you could build a tower 400 kilometers high and stand on top of it, you would weigh nearly the same as you do on the ground. The stability of a satellite is found not in the absence of gravity, but in the presence of velocity. To understand this, we must look at the classic thought experiment proposed by Isaac Newton, often visualized as a cannon firing a projectile from the top of an exceptionally tall mountain. If the cannon fires the ball at a low speed, gravity pulls it downward, and it hits the Earth a short distance away. If the explosive charge is increased, the ball travels further before striking the ground. But if the cannon could fire the ball with enough velocity, a strange transition occurs. As the ball falls toward the ground, the surface of the Earth curves away beneath it at the exact same rate. The projectile continues to fall, but it never arrives. This introduces the first layer of uncertainty into our understanding of spaceflight. A satellite is never truly at rest, nor is it ever securely held by a physical structure. It exists in a state of continuous dynamic tension. To remain in a low Earth orbit, an object must travel at approximately 7.8 kilometers per second. At this speed, a spacecraft can circle the entire planet in about 90 minutes. The line between remaining in orbit and plunging back into the atmosphere or drifting out into deep space is incredibly narrow. It depends entirely on maintaining this precise velocity relative to the mass of the body being orbited. This relationship between speed, mass, and distance is governed by the laws of angular momentum and centripetal force. The gravitational attraction between the Earth and the satellite acts as a central force, pulling the object inward toward the center of the planet. Meanwhile, the satellite's linear momentum drives it to move forward in a straight line. When these two factors are perfectly balanced, the path of the satellite bends into a circle or an ellipse. The satellite is essentially trapped in a geometric valley created by the distortion of space-time around the mass of the Earth, a concept later refined by Albert Einstein in his theory of general relativity. As we look closer at this stable foundation, we begin to see the subtle complications that scientists must resolve. The vacuum of space is not entirely empty. In low Earth orbit, there are still trace amounts of atmospheric gas, thin whispers of upper atmosphere that create an incredibly faint but persistent resistance known as orbital decay. This drag gently slows the satellite down over months or years. As its velocity decreases, the balance shifts. Gravity begins to win the tug of war, pulling the satellite into lower, denser layers of the atmosphere where friction increases exponentially, eventually leading to a fiery re-entry. Thus, even the most stable orbit is a temporary state, a slow-motion fall that requires constant awareness and, occasionally, active correction. To comprehend the nature of this subtle resistance, one must examine the structure of the thermosphere, the layer of the atmosphere that extends from 80 kilometers to approximately 600 kilometers above the surface of the Earth. At these altitudes, the air is so thin that individual molecules of nitrogen and oxygen travel for kilometers before colliding with one another. To a human observer, this environment would appear to be a flawless void. Yet, to a satellite traveling at 7.8 kilometers per second, these isolated molecules become a continuous series of microscopic impacts. Each collision strips away an infinitesimally small amount of the spacecraft's kinetic energy, transferring it as a minute quantity of thermal energy and momentum. This observation introduces an intriguing contradiction in classical orbital mechanics. According to traditional textbooks, an object in motion stays in motion unless acted upon by an outside force. In the conceptual framework of spaceflight, we often treat an orbit as a static mathematical curve traced through a clean vacuum. But the real universe is rarely so pristine. The upper atmosphere does not possess a sharp, distinct boundary where air ends and space begins. Instead, it fades away gradually, transitioning from a dense gas to a ghostly envelope of individual atoms that remains gravitationally bound to the planet. A satellite operating within this region is not truly outside our world. It is navigating the outermost fringes of the Earth's breadth. Scientists actively measure this atmospheric drag using highly sensitive instruments on board small satellites. Through resources coordinated by institutions like the National Aeronautics and Space Administration's SmallSat Information Institute, researchers analyze the subtle decelerations of these miniature craft to construct highly precise models of upper atmospheric density. What they have discovered is that this density is far from constant. It changes based on the time of day, the season, and, most importantly, the activity of the sunday. When the sun undergoes a period of high magnetic activity, it releases intense streams of ultraviolet light and X-rays that strike the upper atmosphere. This sudden influx of energy heats the thermosphere, causing it to expand outward into space like a warming balloon. This solar expansion creates a profound operational challenge for satellite missions. An altitude that was relatively clear of atmospheric particles during a period of solar quiet can suddenly become crowded with gas molecules during a solar storm. A small satellite, which may lack a large propulsion system due to its compact design, can experience a sudden tenfold increase in atmospheric drag. This unpredictable swelling of the atmosphere alters the spacecraft's orbital path much faster than predicted, shifting its position along its trajectory and introducing tracking errors for ground stations. The elegant predictability of orbital physics is thus disrupted by the chaotic dynamics of space weather. The deeper implication of this phenomenon forces us to reconsider the longevity of everything we place into orbit. If the atmosphere is constantly fluctuating, then every object in low Earth orbit possesses a definitive lifespan. A CubeSat deployed at an altitude of 300 kilometers may survive for only a few months before atmospheric drag pulls it down. Conversely, a spacecraft operating at 600 kilometers might endure for decades before the faint whispers of the thermosphere claim it. This variation means that space is stratified by time. The lower orbits are a transient realm where objects pass through quickly, while the higher regions act as historical archives, preserving the machines of previous generations in a silent, slow-motion descent. This reality shifts our focus from the broad concept of planetary geometry to the precise internal engineering required to counteract these forces. To survive the unseen drag of the thermosphere and maintain an orbit long enough to fulfill a scientific mission, a spacecraft must possess an internal architecture capable of sensing, calculating, and correcting its path. This requires a transition from observing the external environment to investigating the silent, mechanical operations that occur within the body of the satellite itself. We must look beneath the solar panels and titanium casings to discover how these machines maintain their orientation, generate power, and communicate across hundreds of kilometers of empty space, leading us directly toward the hidden mechanisms that govern their daily survival. Beneath the elegant geometry of orbital paths lies a complex world of hidden engineering and physical mechanisms that allow a satellite to function as an independent machine. A satellite is far more than a camera or a radio transmitter tossed into the void. It is a fully integrated ecosystem designed to survive one of the most hostile environments known to science. To understand these hidden mechanisms, we must examine the internal architecture of modern spacecraft, particularly the revolutionary shifts highlighted by institutions like the NASA SmallSat Information Institute, which studies how small, highly efficient systems can replicate the capabilities of traditional, massive satellites. The first critical mechanism is attitude, determination, and control. In space, terms like up, down, left, and right lose their meaning. A satellite must know exactly which way it is facing to point its antennas at a ground station on Earth, its solar panels at the sun, or its scientific instruments toward deep space. This is accomplished through a combination of sensors and actuators. Star trackers photograph the surrounding sky and compare the patterns of distant suns to an onboard database, identifying the satellite's orientation with remarkable accuracy. Sun sensors and horizon sensors provide additional reference points relative to the Earth and the solar system. Once the orientation is determined, the satellite must have a way to adjust its position without using up precious chemical fuel. This is often achieved through reaction wheels, which are heavy, motorized discs spinning inside the spacecraft. When the satellite needs to turn, it accelerates or decelerates a reaction wheel. According to Newton's third law of motion, the change in the wheel's angular momentum causes an equal and opposite reaction in the body of the satellite, rotating it smoothly in the vacuum without expelling any propellant. For larger adjustments, magnetic torquers are used, which are essentially electromagnets that interact with the Earth's magnetic field, pushing against the planet's magnetosphere to orient the craft. The history of these discoveries dates back to the earliest days of the space race, when engineers quickly realized that surviving space required mastering the extreme thermal environment. In the vacuum of orbit, heat cannot be transferred through conduction or convection because there is no air. Heat can only move via radiation. When a satellite is in direct sunlight, it is blasted by intense solar radiation, causing surface temperatures to skyrocket to over 100 degrees Celsius. Minutes later, as the satellite passes into the shadow of the Earth, temperatures plummet to -100 degrees Celsius or lower. Managing this thermal shock requires specialized insulation, such as multi-layer insulation blankets made of aluminized mylar, which look like shiny gold foil wrapping the spacecraft. Power generation is another silent marvel operating beneath the surface. satellites rely almost entirely on solar cells to convert sunlight into electricity, which is then stored in lithium-ion batteries for use during the orbital night. In small satellites, this power budget is incredibly tight, often operating on less electricity than a standard household light bulb. Every calculation, every radio transmission, and every sensor reading must be carefully scheduled to prevent draining the batteries. The integration of highly efficient microelectronics has allowed modern smallsats to perform immensely complex computational tasks, while drawing only a fraction of the power required by spacecraft a generation ago. To truly appreciate this delicate energy ecosystem, one must observe the physics of photovoltaic conversion in the raw environment of space. On Earth, the atmosphere filters and softens the light of our star, scattering ultraviolet rays and absorbing specific wavelengths of infrared radiation. In orbit, solar panels are exposed to the full, unfiltered spectrum of the Sun, receiving an unattenuated flux of approximately 1,361 watts per square meter. Yet, converting this abundant light into usable electricity is a surprisingly inefficient process. Standard silicon solar cells convert only about 20% of incoming sunlight into electric current, while advanced multi-junction cells, made from layers of gallium arsenide and indium gallium phosphide, push this efficiency closer to 30 or 40% by capturing different segments of the solar spectrum. This technical reality reveals a fundamental contradiction at the heart of spacecraft design. The very sunlight that preserves the life of the satellite also acts as an agent of its gradual degradation. As solar panels absorb light, they also absorb heat, and as their temperature rises, the efficiency of the photovoltaic conversion drops significantly. Furthermore, outside the protective envelope of our atmosphere, these arrays are bombarded by high-energy protons and electrons from the solar wind. Over months and years, this relentless radiation damages the crystalline lattice of the solar cells, causing a predictable decrease in power output of about 1 to 2% each year. Designers must therefore size the arrays not for the beginning of the mission, but for its eventual end, anticipating a future where the spacecraft must operate on a diminished energy income. To manage this declining resource, engineers rely on sophisticated power management and distribution units. These systems function as the central nervous system of the satellite's power grid, constantly adjusting the electrical load to match the instantaneous generation from the panels. They utilize algorithms like maximum power point tracking to dynamically vary the electrical resistance of the circuit, ensuring that the solar arrays always operate at their peak efficiency, regardless of their temperature or the angle of the incoming sunlight. This precision is especially critical for small satellites, where the surface area available for solar panels is structurally restricted, requiring every single square millimeter of photovoltaic material to be optimized to its absolute physical limit. The deeper implication of this constraint extends beyond the physical arrays and into the realm of time management. Because a satellite in low Earth orbit spends roughly 1/3 of its 90-minute journey enveloped in the deep shadow of the planet, the energy harvested during the sunlit phase must do double duty. It must simultaneously power the active systems of the spacecraft and replenish the chemical energy reservoirs within the lithium-ion batteries. This creates a perpetual cycle of charging and discharging, a rhythmic pulse that dictates the operational tempo of the entire mission. If a satellite miscalculates its orbital position or fails to orient its panels toward the Sun immediately upon exiting the shadow, the batteries will deplete past a critical threshold, leading to a state of unrecoverable systemic dormancy. This reliance on cyclical energy storage introduces a profound element of uncertainty regarding the longevity of micro spacecraft. Lithium-ion batteries possess a finite cycle life, meaning that after thousands of rapid charges and discharges, their internal chemistry begins to degrade, reducing their total capacity to hold a charge. In the miniature architecture of a modern CubeSat, replacing a failing battery is impossible. The machine must survive on what it has, navigating the fine line between power generation and thermal survival in an environment where a single component failure can cause the entire system to go dark. This endless balancing of energy budgets highlights a larger puzzle about how these miniature platforms maintain their stability while executing complex instructions. A satellite cannot simply collect power. It must use that power to stabilize its body, point its instruments, and resist the subtle gravitational disturbances that threaten to spin it out of control. This shifts our investigation from the generation of electrical energy to the manipulation of physical forces, leading us toward the invisible structural variations of the Earth itself and the elegant, counterintuitive methods spacecraft use to maintain their orientation without ever touching solid ground. As our understanding of these mechanisms deepens, we encounter the first major contradiction in satellite operations: the problem of orbital perturbations and non-spherical mass distribution. In classical physics textbooks, the Earth is treated as a perfect, uniform sphere with a gravitational field that pulls equally from all directions. If this were true, a satellite's orbit would remain completely fixed in space, tracing the exact same path indefinitely. But the real Earth is an oblate spheroid, flattened at the poles and bulging at the equator due to its centrifugal rotation. It is also lumpy, with vast variations in density within its crust, mantle, and oceans. This asymmetrical distribution of mass creates a gravitational field that is dynamic and uneven. As a satellite passes over the equatorial bulge, it experiences a subtle, extra tug of gravity that slightly alters its trajectory. This phenomenon causes the plane of the satellite's orbit to slowly rotate over time, a process known as nodal precession. To the early pioneers of space tracking, this deviation looked like an error in their calculations, a contradiction between theoretical orbital mechanics and observed reality. However, instead of fighting this perturbation, orbital mechanics discovered a way to utilize it. By launching a satellite into a very specific angle relative to the equator, known as a sun-synchronous orbit, engineers can match the rate of nodal precession with the Earth's orbital speed around the sunday. The result is a fascinating paradox: a satellite whose orbital plane rotates at the exact same rate the Earth moves through its yearly journey. Consequently, every time the satellite passes over a given point on the Earth's surface, the Sun is at the exact same angle in the sky. This allows scientists to compare images of the planet taken weeks, months, or years apart without having to compensate for changing shadows, creating a consistent visual record of environmental change. Yet, this solution introduces another puzzle. The uneven gravity of the Earth is not the only force disrupting the satellite's path. Solar radiation pressure, the actual physical force exerted by photons streaming from the sun, strikes the satellite like a gentle wind hitting a sail. While this force is incredibly small, over weeks and months, it pushes the satellite out of its intended alignment. Additionally, the gravitational influence of the Moon and the Sun continuously tugs at the spacecraft, creating a complex multi-body problem that cannot be solved with simple equations. Satellites must therefore engage in a practice called station keeping, using minuscule amounts of thrust from ion engines or chemical propellants to constantly fight these cosmic influences, expending energy simply to stay in place. To observe the mechanism of solar radiation pressure is to engage with one of the most elegant and subtle principles of quantum mechanics. Photons, the fundamental particles of light, possess no intrinsic rest mass, yet they carry momentum. When a photon emitted by the nuclear furnace of the Sun travels through the vacuum of space and strikes the surface of a satellite, it transfers this momentum to the spacecraft. If the surface is highly reflective, like the silver multi-layer insulation wrapping an instrument bay, the photon bounces off, transferring twice its initial momentum in the process. This microscopic exchange, multiplied by the countless octillions of photons streaming from the Sun every second, creates a continuous, predictable force. At the distance of the Earth's orbit, this pressure amounts to only about 9 micronewtons per square meter, a force so gentle it could not lift a single grain of sand on Earth, yet in the frictionless void of space, its cumulative effect is absolute. This continuous photonic bombardment creates a profound contradiction for missions requiring high orbital precision. We often treat the Sun merely as a source of thermal energy and electrical power, an external asset that sustains the machine. However, from the perspective of orbital dynamics, the Sun is also a cosmic disruptor, acting as a constant, low-intensity thruster that pushes the satellite away from its mathematically ideal trajectory. If a satellite is asymmetric, with large solar arrays extending from one side and a compact instrument bus on the other, the solar radiation pressure will strike the spacecraft unevenly. This offset creates a persistent rotational torque, causing the satellite to slowly spin out of its alignment. Left uncorrected, this light-driven torque will eventually overwhelm the internal reaction wheels, forcing the spacecraft to waste valuable resources simply to remain facing the correct direction. To explain and manage these orbital disruptions, orbital mechanics must look beyond the simple two-body equations first formulated by Johannes Kepler. In the real environment of low Earth orbit, a spacecraft exists within a complex gravitational matrix. While the Earth remains the dominant gravitational anchor, the Moon and the Sun exert their own independent pulls. Because the distances and angles between the Earth, the satellite, the Moon, and the Sun are constantly changing as they move through their respective orbits, the net gravitational force on the satellite is in a state of continuous, non-linear flux. This scenario is a practical manifestation of the multi-body problem, a classic mathematical challenge that cannot be solved with an exact algebraic formula. Instead, supercomputers must run continuous numerical integrations, predicting the satellite's future position by calculating these overlapping gravitational vectors step by agonizing step. The deeper implication of this constant battle against solar pressure and multi-body gravitation shifts our understanding of what it means to be in space. An orbit is not a permanent track carved into the fabric of the universe. It is a dynamic, shifting path that must be actively defended. This defense, known as station keeping, requires a sophisticated interplay between orbital tracking, computational trajectory modeling, and propulsion engineering. For traditional, heavy satellites, this meant carrying massive chemical propellant tanks, using hydrazine thrusters to periodically blast the spacecraft back into its proper slot. For modern small satellites, however, carrying large volumes of volatile chemicals is structurally impossible, forcing a reliance on highly efficient, low-thrust alternatives like electric ion engines or cold gas thrusters. This reality introduces an enduring uncertainty that challenges the long-term planning of deep space and near-Earth operations. Every time a satellite fires its thrusters to correct its orientation or counteract the gravitational pull of the Moon, it consumes a non-renewable resource. Even the most advanced ion engines, which accelerate noble gases to hypersonic speeds using solar electricity, will eventually deplete their propellant reserves. The moment the onboard fuel is exhausted, the satellite loses its ability to fight the relentless pressure of solar photons and multi-body perturbations. The universe begins to reclaim the machine, slowly twisting its orientation and warping its orbital path. This continuous need for active trajectory correction highlights a larger, systematic complication as we move outward from single, isolated satellites to large-scale operations. If a solitary spacecraft requires continuous monitoring and thrust to maintain its alignment against these subtle cosmic forces, the complexity scales exponentially when hundreds or thousands of these machines must operate in perfect synchronization. The challenge transitions from managing the physical survival of an individual instrument to coordinating the collective behavior of an entire artificial network. This carries our investigation into the modern frontier of distributed space architectures, where the boundaries between independent machines begin to blur, forcing us to explore how massive constellations of small sats navigate the increasingly crowded and complex environment of low Earth orbit. As we venture further along this road of inquiry, the simplicity of satellite mechanics breaks down entirely when we confront the scale of modern constellations and the growing density of the orbital environment. For decades, space exploration was defined by large, solitary spacecraft acting as isolated outposts. Today, organizations like the NASA SmallSat Information Institute track a profound shift toward distributed space architectures, where hundreds or even thousands of small satellites operate together as a coordinated network. This transition introduces deep complexities regarding automated navigation, communication latency, and the limits of our ability to track objects in motion. When thousands of satellites are placed into low Earth orbit, the risk of collision ceases to be a theoretical abstraction and becomes an urgent statistical reality. Every satellite moves at hypersonic speeds, meaning that even a fragment of paint or a stray bolt traveling in an opposite orbit carries the kinetic energy of a speeding automobile. If two satellites collide, they do not simply break. They disintegrate into tens of thousands of untrackable fragments, each moving on its own independent orbital path. This scenario, known as the Kessler syndrome, presents a terrifying possibility. A cascading chain reaction of collisions that could render specific orbital regimes entirely unusable for generations, surrounding our planet in an impenetrable shell of high-speed debris. To prevent this, scientists face a profound challenge in computational physics and observation. Tracking objects in orbit requires a worldwide network of radar systems and optical telescopes. However, the position of a satellite cannot be known with absolute certainty. Atmospheric drag fluctuations caused by solar storms, which heat and expand the upper atmosphere, introduce variables that make predicting a satellite's path days in advance incredibly difficult. Having acknowledged the echoes of the past, we now move past the single, mysterious particle and delve into the quiet, fundamental arena where all these strange behaviors originate, the quantum field. This is the deeper structure of reality, the concept that transforms the universe from a space containing particles into a space entirely filled with dynamic, underlying fields. Image illustrating the concept of a quantum field, perhaps with ripples or excitations on a subtle surface. Imagine that every type of fundamental particle you have ever heard of, the electron, the photon, the quark, is not a tiny, discrete marble flying through empty space. Instead, imagine that the entire universe is pervaded, everywhere, by a corresponding, continuous, invisible field. There is an electron field, a quark field, a photon field, and so on. These fields are the true, foundational reality. Space is not empty. It is a plenum, quietly vibrating with potential energy. A particle, in this new, deeper structure, is merely a localized excitation, a ripple, or a tiny, quantized vibration in its respective field. An electron is a hump, a precise quantum of energy vibrating in the omnipresent electron field. A photon, a packet of light, is a ripple in the electromagnetic field. This concept, known as quantum field theory, or QFT, is the modern, powerful language that describes all fundamental physics, and it quietly restores a kind of continuity to the Heraclitean flux. The flow is not just of probability, but of the field itself. The implications of this fundamental reality are profound. If you look at what we once considered empty space, the vast gulf between the electron and the nucleus of an atom, or the dark vacuum of interstellar space, you realize that this space is, in fact, incredibly active. It is constantly roiling and churning with microscopic, instantaneous quantum activity, the quiet, subtle manifestation of the uncertainty principle. The Heisenberg uncertainty principle does not just apply to a particle's position and momentum, it also applies to another complementary pair, energy and time. This means that for a fleetingly short period of time, the amount of energy in a tiny volume of space can be momentarily uncertain. This uncertainty allows for the spontaneous, instantaneous materialization of what physicists call virtual particles. These are particles that exist for such a minuscule, immeasurable fraction of a second, a time period so brief that the particle refuses to make eye contact with our most sensitive detectors, that they do not violate the fundamental law of energy conservation. Picture the vacuum now, not as stillness, but as a vast, quiet sea of activity. Pairs of virtual particles and antiparticles, say, a virtual electron and a virtual positron, spontaneously erupt into existence from the energy of the field, separate for an instant, and then just as instantaneously annihilate one another, returning the borrowed energy to the vacuum. This constant, furious, subtle dance is happening everywhere, all the time, beneath the calm surface of perceived reality. This concept of virtual particles, of the vacuum being a dynamic, bubbling broth of potential, provides the physical mechanism for all fundamental forces. When two real electrons interact, they do not simply touch or hook together in the Democritean sense. Instead, they exchange virtual photons, which are the quanta of the electromagnetic field. One electron emits a virtual photon, which is then absorbed by the other electron. This exchange of the virtual particle mediates the force, creating the repulsion that keeps the two electrons apart. The strong nuclear force, which holds the nucleus together, is mediated by the exchange of virtual gluons. The field is the quiet architect of force. The particles are just the points where the field's energy has localized. This realization completely reframes the nature of both matter and force, unifying them into the single concept of field excitation. We see that the non-local correlation of entanglement is simply the shared, indivisible nature of the field itself, the background substrate refusing to be cut into separate pieces. The concept of the quantum field also introduces a new kind of subtle, dry humor. The universe is constantly trying to borrow energy from nothing, only to have to pay it back instantly, like a tireless, silent financier operating at the most minuscule scale of time. This quantum foam is the source of a tiny, measurable energy known as the Casimir effect, another experimental anomaly where two perfectly uncharged parallel metal plates placed incredibly close together in a vacuum, are quietly pushed toward each other by the imbalance of virtual particles outside the gap versus those that can fit in the smaller gap between them. This quiet, measurable force is direct evidence of the field's subtle activity, the vacuum pressure of the cosmos. As we conclude this exploration of the deep structure, we realize that the universe, at its core, is a vast, interconnected web of energy fields, perpetually in flux, governed by a beautiful, precise mathematical language. The solidity we perceive is an illusion of scale, merely the macroscopic average of countless, simultaneous virtual eruptions and annihilations. We have moved from the single hesitant particle to the universal field. This expansive view now necessitates a turn back to the human scale, asking the quiet, final question: how does this profound structure, this sea of potentiality and chance, reflect back on the mind that observes it? We move into the arc of the human reflection, asking about the nature of perception and consciousness in a fundamentally probabilistic universe. We are left standing at the boundary of an unfinished question, looking out at a universe that remains beautifully incomplete. String theory has provided us with an elegant bridge across the great divide of modern physics, offering a way to harmonize the smooth geometry of gravity with the chaotic probabilities of the quantum world. It has revealed a breathtaking vision of reality, where the matter that composes our bodies and the forces that guide the stars are all woven from the same fundamental music, vibrating through a hidden labyrinth of extra dimensions. This introduces a profound contradiction to our daily experience of existence. Everything we perceive is defined by where it is and when it happens. To strip away space and time feels like stripping away the very capacity for anything to exist at all. Yet, when physicists study the quantum equations of string dualities, they find that space can radically change its shape, or even tear and repair itself, without causing any disruption to the underlying physical laws. The smooth geometry we navigate appears to be a fragile mask. The explanation for this emergent reality lies in the behavior of quantum entanglement and the collective dynamics of fundamental strands. Just as the sensation of a solid, smooth marble table emerges from the collective electrostatic forces of trillions of vibrating atoms, the sensation of a three-dimensional room emerges from the complex, non-local correlations of strings. This leaves us with a haunting remaining uncertainty that challenges the limits of human comprehension. If space and time are emergent properties, what is the nature of the true, timeless, and spaceless medium that exists beneath them? We lack the language, the mathematics, and the sensory intuition to describe a reality where there is no here, no there, no before, and no after. We are like sailors trying to understand the deep ocean currents solely by watching the patterns of the waves on the surface, conscious that a vast, silent world operates completely out of our sight. This realization forces a deeper reflection upon the tools we use to investigate the cosmos. For centuries, our primary tool has been reductionism, the belief that to understand a complex system, you must break it down into its smallest individual pieces. We broke matter down into molecules, molecules into atoms, atoms into subatomic particles, and finally, particles into strings. But at this ultimate boundary, the distinction between the piece and the whole begins to blur. Because of the dualities inherent in string theory, shrinking a dimension past a certain minimal size yields a universe that is mathematically identical to a universe where that same dimension is infinitely expanding. The ultra-small and the ultra-large meet in a perfect closed loop. This geometric inversion implies that our quest for the smallest fundamental building block may be an artifact of an incomplete perspective. Nature does not appear to have an absolute bottom layer. Instead, it possesses a deep structural holism where the macrocosm and the microcosm mirror one another. The boundary between the observer and the observed, between the container and the contained, becomes fluid. The search for the hidden architecture of the universe remains a continuous, living investigation. It lives in the quiet mathematics of researchers working late into the night, tracing the vibrations of invisible strands across 10 dimensions. It lives in the silent processing of data from deep space observatories, searching for the faint cosmic echoes of the Big Bounce. And it lives in the reflective stillness of our own minds, as we contemplate our place within a cosmos woven from pure geometric music. The music continues to play, echoing through the large dimensions of the night sky and within the tightly curled channels of the microscopic world, carrying our understanding forward into the patient, unfolding dark.